Now I'm going to choose red LEDs to show conduction when the top rail is positive with respect to the bottom rail. So we remove this diode temporarily and insert a red LED on the half-wave rectifier. We remove the two diodes that will conduct when this is the positive and this is the negative. So this LED, if this is positive, it can't go through this diode. It can go through this diode. We'll power the LED and return to the negative side through this diode because this diode is reverse biased. So we're going to remove this diode and this diode and replace those with red LEDs as well. To show the negative half cycle, where this rail is positive with respect to this rail, I'm going to use green LEDs and put the first green LED here and the second green LED here when it conducts this direction. Now I'm going to make one more modification to this circuit. What we're going to do is we're going to insert into the complete circuit an additional LED, but it's a special LED. It's a bicolor LED, and it only has two legs. It looks like a completely normal LED that would just turn on to some arbitrary color with a diffuse output. But inside this LED is actually two LEDs. One is red, one is green, and they're oriented opposite each other. So when unlike other LEDs and diodes, which will only conduct in one direction and block current flow in the other direction, a bicolor LED will turn one color when it conducts in one direction and turn another color when it conducts in the opposite direction. And I'm going to pop it in at the very beginning of the circuit, essentially right here. I'll do that by moving this conductor to the other rail and then tying the two rails together through that LED. And I'll reconnect the oscilloscope to the AC input using jumpers on the opposite end of the rail. Not for any really important reason other than to keep the probes off to the left of the board instead of sitting on top of everything that we want to see. So if we now turn on the function generator, because there is no negative half cycle, because there is no positive bottom rail with respect to the upper rail, the only path that current ever flows in this circuit is from the top rail through this diode, through our load, through this diode, and back. So we're seeing this light up, this light up, this light up. If I do nothing more than reverse the connections right now, so that instead of having a positive and a 0 volts and a positive and a 0 volts, we have a negative and a 0 volts and a negative and a 0 volts. You'll see the difference. So now the bottom rail is positive with respect to the negative rail when it's conducting. The current flow has gone in the opposite direction through our bicolor LED, so the bicolor LED is showing as green. The half-wave rectifier is not able to conduct because it only has one diode, but the full bridge is now conducting through the opposite pair of diodes, this one and this one, which are forcing the current to still go from left to right through our load, making this the positive at all times, this the negative at all times, regardless of whether this or this is positive or negative. Now, with the input source having its polarity reversed, you might have noticed not only that the waveform is now below 0 instead of above 0, showing that it's a negative half cycle with respect to the ground clips, but you'll also notice that the waveform is traveling again. It's traveling across the oscilloscope screen because the trigger level that we set when it was positive is now above and off of any part of the waveform. So the oscilloscope is waiting for a trigger, but it only waits for so long before it decides to sweep anyway. And its frequency of sweep is a little bit out of sync with the frequency of the waveform that we're feeding it. So it's moving in time. Easy change, trigger level, bring it down onto the waveform, and now we will have another solid, stable waveform that's being triggered at the middle of the screen. Put it back the way it was originally. Bring the trigger level up. And now we're going to do two things. One is I'm going to turn on the measurement cursors. They're already on. I'm going to move the measurement cursors to the voltage level that I want. And the voltage level that I want is a positive and negative 16 volts to match the AC transformer's output. So we'll take the first and bring it up to 16 volts on the screen. As a guide, by the way. This is not affecting the input, it's just a guide for us. Change to Y2, bring it down to 16 volts. And now on the function generator itself, I'm going to adjust the offset, the DC offset, and the level in order to get this waveform plus and minus 16 volts centered on the 0 volts. And as you're watching the waveform move around on the screen, you can also watch the board and how the LEDs change. Now, you'll also notice that although we have a positive and negative polarity, we have an actual AC waveform with a wave shape that is a square, not a sine wave. You'll notice that the half-wave rectifier is conducting and lighting up the load. The full-wave rectifier is not. There's two reasons for that. One is the voltage is much lower, so with the voltage lower through the same resistances, the current is going to be lower and the LEDs won't be as bright. The reason that the full bridge isn't conducting at all is because each of these LEDs requires, I think, about 2.5 volts to conduct. So the minimum that this is going to need to even turn on is 2 volts through the first LED, 2 volts, actually 3 volts through the blue LED, and an additional 2 volts through the second rectifier LED for a total of 7 volts. And if you look on the screen, we have a 5 volt per division vertical scaling, and we're only barely above 5 volts. Let's say 6 volts. It looks like it's plus and minus 6 volts right now. So now we increase the amplitude. And as soon as we are above the sum of the forward voltage drops, you now have conduction in both directions. Now, unfortunately, the function generator doesn't seem to be able to go above plus and minus 10 to 11 volts, which is enough to make the circuit work, but it's not enough to match the 16 volt peaks that we have on the AC transformer. So we'll go back to the AC transformer after a few more notes. The first note is the output from the function generator is a square wave. It's going from plus 10 to minus 11 volts. We could change the offset a little bit, but I'm not going to worry about it right now. The point is that being a square wave, it snaps from the positive cycle to the negative cycle full voltage. Plus 10, minus 10, plus 10, minus 10. You can see that in the behavior of the LEDs. They are snapping on and off instead of smoothly transitioning. If we now change the type of waveform that's coming from the signal generator to a sine wave, just to make it clearer on camera, I'm going to reduce the frequency even more. You can very clearly see that with a sine wave, because the voltage gradually transitions from the positive cycle through 0 to the negative cycle through 0, the increasing and decreasing voltage causes an increasing and decreasing light. You'll also notice that the LEDs are not continuously on. There is a very definite period where the red LED is on, nothing is on, green is on, nothing is on, back to red. So right now the frequency is quite low. It's not even 1 hertz. It looks to be about 0.5 hertz. 1 cycle per 2 seconds. We're going to ramp this up gradually toward 60 cycles per second. So now at this point we have an AC waveform that is a sine wave. I'm going to switch the trigger back to 0 volt, and I'll just get rid of the measurement cursors for the moment. So the half-wave rectifier is only conducting on the positive half cycle. So it's blinking 60 times per second here and 60 times per second here. On the full bridge rectifier, each pair of diodes is conducting 1 half cycle, but the pairs are together conducting both half cycles to the blue LED. So while the red and the green LEDs are each blinking 60 times per second, the blue LED that is conducting on both half cycles is actually flashing 120 times per second. Now, while it's certainly much more pretty to have all of these LEDs blinking and lit up, it's also very wasteful for 2 reasons. One is the LEDs are only allowed to conduct up to 20 milliamps before they start to overheat and die. Rectifier diodes, the 1N4000 series, can conduct up to an amp. The second is that each of these LEDs contributes a voltage drop to the circuit. And below that minimum total voltage drop for all of the diodes in the circuit, nothing happens. From a design standpoint, that is horribly wasteful. So we're going to do all of the next experiments and the next analysis with the actual AC transformer And I'm going to change all of these LEDs that I inserted for demonstration purposes back to the original rectifier diodes.